All right, 7th graders, we are in section 6.5. You have had to do a lot of equation solving since elementary school. However, this is going to be a first for you. You are now going to solve exponential equations. So what does that mean? What does it mean to solve exponential equations? It's more than just solving equations with exponents. It's actually going to be solving equations with the variable as the exponent. So before we begin, let's figure out what are we going to learn. We're going to learn how to solve exponential equations 3 different ways. We're going to learn how to solve them using the same base, but first being given unlike bases, and then sometimes you can't use either one of these. We're going to have to solve by using your graphing calculator. So let's start with solving exponential equations with the same base. These are the easy ones. Exponential equations are equations in which the variable expressions occur as exponents. Just like I told you, the exponents are your variables. Your core concept. Here's your core concept. Properties of equality for exponential equations. So in words, here's what it says. 2 powers with the same positive base b, where b is not 1, are equal if and only if their exponents are equal. So here's what it looks like. You're like, I have no clue what that means. Here's what it looks like. You'll notice here, and I'll rewrite it and point to what I'm talking about. This right here is your base. A base of 2, a base of 2. They're the exact same base. So if you have the same base, then your exponents are equal. So in this case, if 2 to the x power equals 2 to the 5th power, then x just equals 5. So if x equals 5, then 2 to the x equals 2 to the 5th. So this is where if and only if comes in. If and only if is something you're going to learn in geometry, but it works both ways. So it says if 2 to the x is equal to 2 to the 5th, then x equals 5. And if x equals 5, then 2 to the x equals 2 to the 5th power. Algebra says if b is greater than 0. It's important to note that your base b has to be greater than 0. It cannot be 1 because 1 to any power is just 1. So then b to the x equals b to y if and only if x equals y. So we're going to start with our first examples. These all have the same base. You'll notice that example 1 and A, B, and C all have the same base. So all you do is if the bases are the same, then your exponents must be the same as well. So all you would do in A is set the exponents equal to each other. X plus 1 equals 5, and then you'd subtract 1 on both sides, so x equals 4. In this case, the bases are the same. You'll notice that this one has no power written, but remember, that means that that's a power of 1. So you would write 1 equals 2x minus 3. You'd add 3, divide by 2, simple equations to solve. X is going to be equal to 2. In the last one, your bases are the same. So you set your exponents equal to each other. Now we subtract 2x, you get x equals 3. This is the easy one. Exponents with the same base are incredibly easy. All you do is set the powers equal to each other. So here's the hard part. The hard part is solving exponential equations with unlike bases. So to solve some exponential equations, you must first rewrite, here's your key concept right here, rewrite each side of the equation using the same base. You must make them the same. You absolutely must make them the same. So in A, we have 5 to the x power equals 125. You will notice, now first of all, you're going to look at this and go, Mr. Humphreys, really? 5 to what power gives me 125? I know that's 3. Yeah, you're right, it is 3. But they're not all going to be that easy. You have to make both bases the same. So in A, how could you rewrite them with the same base? Well, 5, we could just leave alone. And then 125, we could also use a base of 5. We could rewrite it as 5 to the power of 3. They're the exact same base. Now, because they're the same base, I can just write x equals 3. because the powers, or the exponents, are now the same. B, 4 to the x power equals 2 to the x minus 3. We do not have the same base, but I can make both bases 2. Well, the first one is going to be, how could I rewrite 4? Well, 4 can be rewritten as a base of 2, 2 to the second power. But then the x is still there, equals, the right side doesn't change, 2 to the power of x minus 3. So now the bases are the same. I set my exponents equal to each other. Solve your equation. X equals negative 3. And the last one. 9 to the x plus 2 equals 27 to the x power. I have to make their bases the same. Hopefully you can look at this and say, well, I can make both of these have a base of 3. So 3 to the second power gives you gives you 9. You'll notice I'm putting this in parentheses because the x plus 2 is your exponent. I am just taking the 9 and rewriting it as 3 squared. Now, you could have done the same thing over here. Now, 27 could be rewritten as 3 to the third power to the x. But here's where you have to follow your rules that you learned a while back. Power to a power. Power to a power, you multiply. So this becomes 3, and then you have to multiply 2 times the quantity x plus 2. That will give you 2x plus 4 equals 3 to the 3x. My bases are now the same, so my equation would be 2x plus 4 equals 3x. I subtract 2x on both sides, and that gives me the value x equals 4. Now these are going to be different. In example 3, you'll notice that we have fraction bases, which means I have a base that's in between 0 and 1. So you have to find out, once again, how you can write these with the same base. This is a little tricky. So, how could you rewrite 1/2 and 4 as the same base? I'm going to make you think about it. What base could 1/2 and 4 be written as? Hopefully, since you're talking about fractions, you realize that you can write them as negative powers. So 2 to the negative 1 power, remember we take the inverse, so 2 to the negative 1 power becomes 1/2. And, I'm going to rewrite this here, that'd be 2 to the negative 1 power to the x equals 2 squared. Now, power to power, I multiply, so that gives you 2 to the negative x equals 2 squared. Bases are now the same. Negative x equals 2. Divide by negative 1. My x value would be negative 2. So try to do the next one by yourself. How could I rewrite 4 and 1/64? Now, you could rewrite them as a base of 2. But 4 to the third power does give you 64. So you could leave it as 4 to the x plus 1. But 4 to what power would give you 1/64? Well, I'm going to actually take one extra step here and write it up here. I'm hoping you see that 1 over 4 to the third would give you 1/64. But if I rewrote it with a negative exponent, it would be 4 to the negative third power. So now I have the same base. X plus 1 equals negative 3. X equals negative 4. Now you can completely skip over all of these if you want. I'm going to give you 7 examples that you can do on your own, extra practice. But in about 5 seconds, I'm going to pop up the answers. Here are some extra examples for you for extra help. And they're going to disappear right now. Lastly, we're going to solve them by doing graphing. Here's the problem. Sometimes it is impossible to rewrite each side of an exponential equation using the same base. You can solve these types of equations by graphing each side and finding the points of intersection. There's your steps right there. Graphing each side, finding the points of intersection. Exponential equations can have no solution, one solution, or more than one solution depending on the number of points of intersection. So if you had a line intersect a parabola twice, then you would have two answers. So example 4, we're going to graph both of these. Now we're going to start with A. A, you'll notice right here, has a base of 1/2 and 7. I cannot rewrite those with the same base. So here's how you start. You're going to take each side of your equation. So for example, I'm going to take this right here. 1/2 x minus 1, and I'm going to put a y equals that 1/2 to the x minus 1. Then I'm going to take the right side, and I'm going to say y equals 7. You basically say y equals each side of the equation, and you're going to just punch them into your graphing calculator. So once again, when you plug them into your graphing calculator, remember, you can use zoom fit. You can use the functions to make sure that it appears in the window, the intersection. So you enter both equations into your graphing calculator. You hit graph, make sure that it's in the viewing window where it shows where they intersect. Now, looking at it, how many times does this graph intersect? It intersects once. So what you have to find what that is, because you can't just guess. You're going to use the intersect feature, which I'll show you how to do that in class. But we're going to use the intersect feature, and it's going to tell you where they intersect. So these graphs intersect at approximately -1.817. So once again, though, we only need the value of x. Remember, your original equation only has an x in it. So I only need the x value. So your answer is approximately -1.81. And in our last example, B, we take each side, y equals 3 to the power of x plus 2, and y equals x plus 1. We graph both of them. We enter them in a calculator. The graph of the equations in the viewing window shows where the graphs could intersect. So what can you tell me about where these graphs intersect? They don't. Therefore, this has no solution. Your equation has no solution.